All right, in this video, I'm going to be going over linear algebra homework 1.2, but this is just going to be more examples of, lines and planes in space problems, okay? So let's start off with the first one. It says, I'll show it to you. Write a vector equation for line L, the line that passes through two given points, okay? 2 points, write the line through. We can do that. Okay. So I'm going to put P here, Q there. This is 0, 4, 1. That's 1, 2, 4. Okay, so we're going to need a vector in between them. And that's going to be V equals X increased by 1, Y decreased by 2, and Z increased by 3. Okay, so an equation for L is going to be, ask for a vector equation, but that's pretty much how we're going to write it in this class. You can pick either of them, right? I'll just choose P. So 0 plus 1t, 4 minus 2t, and 1 plus 3t. Okay. At t equals 0, L is at point P, right? 0, 4, 1. When t equals 1, notice that's where we're at point Q. Okay. That's going to be just like the easiest way to parameterize our line. Okay, now we're going to consider a line M defined by x equals 3 plus 2t, y equals 2 minus t, and z is 1 plus 3t. Okay, and we're going to write an equation for a line parallel to M, but not the same as M. Okay, yeah. Okay, so parallel means it's going to, like in Algebra 1, meant to have the same slope. This is kind of like our slope. It's our direction numbers. So we're going to want the same direction numbers, but maybe different, like different intercept. So maybe you can see that yeah, this does not go through the origin, because if it did, then it would need to be like 0 simultaneously, and this is going to be 0 when t equals 2, and when t equals 2, that is not 0. So let's just write for one parallel. Let's write one that goes through the origin, right? So that would be, parallel would be 0 plus 2t, 0 minus t, and 0 plus 3t. And that's going to be a parallel line. Okay. Then we're going to write a different equation for a line with the same path as M. Okay, so what we need to, we're just basically going to reparameterize it. Well, I think the easiest way to do that is that if M is equal to, 3 plus 2t, 2 minus t, and 1 plus 3t, if we just wanted this to, trace faster, we could make it go twice as fast. We could make this 4t, negative 2t, and 6t. Okay, that's an option. We could reorient it in the opposite direction. This is going to have like kind of a sense of direction with increasing t. It's going to go along a line in a particular direction. If we wanted to reverse it, we could just say 3 minus 2t, 2 plus t, and 1 minus 3t. And then, your old t's would become my new negative t's or whatever. Okay, so I'll just say M alt. You got a couple of options I just told you, but, maybe I'll just say 3 plus 4t, 2 minus 2t, and 1 plus 6t. I just made it go twice as fast. Number 3, we want a vector equation for a line that passes through P0 and is normal to the given plane. Okay, so we need to get a normal vector off of this plane, and then hopefully we can just say goes through that point, has that direction that's going to be the same as that normal, and we can just write an equation for the line. Okay, so what was I thinking? Okay, just going to draw a picture, I guess. All right, so I'm going to just draw P0 here, with no loss of generality, and I'm going to call it 1, 2, 1. And then I'm just going to say, the plane is everywhere, so maybe it's just part of it is right there. And we've got some normal vector that happens to be right underneath. Okay, it seems to be originating from right underneath P0. And that's okay, right? Because the normal vector is just a vector and we can move it around on the plane. Okay, so the normal vector for the plane 3x plus 4y minus 1z equals 9 is going to be 3, 4, negative 1. You just read it right off of the equation for the plane. Okay, and so if we've got a point in a direction, we can write an equation for this line. So this, line is going to be something like f of t equals 1 plus 3t, 2 plus 4t, and 1 minus t. Okay. And then, okay, for number 4, find the point P where the given line intersects the given plane. Okay. There's 2 of these, so I don't know if I'm going to be able to fit it on this sheet. Let's just move on. Okay, so L1 is 1 plus 2t, 3 minus t, and 5 plus 4t. And then the plane is x plus y minus z equals 2. Okay. This is not an example I did in class, but I think hopefully you can kind of figure out what to do, right? We can say, okay, well, this is x, that's y, that's z. If it's going to intersect, then it's going to satisfy this as well, because it's going to be on the plane. So we can just say, I'm going to need to go over here, say x is 1 plus 2t, plus y is 3 minus t, minus z is 5 plus 4t, that's equal to 2. And then we're just going to solve for t, I think, right? The point P, and then once we find that, we could plug it in and find coordinates. And I think it would be easiest to plug it in to L of t, right? Anyway, okay, so I'm just going to count the t's. I've got 2 minus 1 is 1, minus 4 is negative 3. And then, my numbers, I've got 1 and 3 is 4, minus 5 is negative 1. So I'll have 3t minus 1 equals 2. I'm going to add over negative 3t equals 3t is negative 1. Okay. And then the point P is going to be just, really L1 of 1. I could say that. Of negative 1. Whoops. And that's going to be the vector. I plug in negative 1 for t here, so I get 1 minus 2 is negative 1. 3 minus negative 1 is 4, and 5 minus 4 is 1. Okay. So I'm going to do that again for part B. I think, if memory serves, B is not going to intersect somehow. I think I went and made sure to choose one where the given line would not intersect the given plane, which would mean that they were in some way parallel. Right? Yeah, I don't think it would make sense to say the line would be skewed to the plane. Yeah, we would just say it's parallel. Okay, so L2 is given by 4 plus 2t, 7 plus 2t, and 5 plus 4t. Okay, plane is the same as x plus y minus z equals 2. So we're going to go down there and do the same thing. X plus y minus z equals 2. Okay. Now that would be, hold on. Yeah, I'll just do the numbers first. 4 plus 7 is 11, minus 5 is 6. Then I've got 2t plus 2t is 4t, minus 4t is 0. So that's 6 equals 2. And that doesn't ever happen. So we're saying that this line intersects that plane as often as 6 equals 2, which is to say never, right? So it does not intersect. Okay. If we had gone through all of this And suppose this had been the plane x plus y minus z equals 6. Okay. Well, if that was equals 6 and we had 6 equals 6, that would be evidence to you that this line sat inside that plane. Okay. But I didn't do one of those. That might have been smart. Maybe next year. So for number 5, this is plane through 3 points. Okay, this is a very standard type of 3D algebra problem, right? So we got PQR, and I'm going to just draw a little sketch. Copy the points. 1, 0, 3, 2, 1, 5, and 1, 4, 4. Okay, I generally like to choose the least of, the coordinate set that has the lowest numbers in some way, so that my vectors can be mostly positive numbers, so that when I take the cross product, I'm less likely to make an error. So I'm gonna start originating from P. I'm gonna go PQ and PR. Okay, and so this, as you can see, it's starting to look more like a plane once I add these vectors in, especially if I was to do that, right? Let's see, this is starting to look like a plane. And we can get the normal vector for the plane by crossing these two, right? I can say that, let's get a quick pen, that this normal vector N is at least proportional to PQ crossed with PR. It looks like actually N is going to be looking like PR crossed with PQ, considering right-hand rule stuff. So I'm going to also say that N is equal to, well, I need to actually write, let's say PR crossed with PQ. Just write it like that. Okay. But I need to write what PR is. Okay, so PR is going to be, I increased nothing in X, 4 in Y, and 1 in Z. And PQ is going to be, I increased 1 in X, 1 in Y, and 2 in Z. Okay, so hopefully these are going to be, easy enough to cross. All right. Let's see, so it's going to be 8 minus 1 is 7, 0 minus 1 is negative 1, and 0 minus 4 is negative 4. All right, and I'm going to say that this is 7, 1, negative 4. Okay, so now that I've got a point and a normal, I'm going to just use the point normal form. So the the equation for the plane is going to be 7 times x minus 1. Maybe I'll call it x minus 2. Doesn't matter. Plus times y minus 1, if I'm going to use this point, minus 4 times z minus 5. That's equal to 0, right? Because it is the set of all points where n dotted with these vectors is 0. Okay. All right, that's number 5. Number 6 is the planes are intersecting in a line. Write a vector equation for the line. Okay. All right, I'll be honest, I had to remind myself how to do this one. I had to work it off to the side before I did it for you. So we've got 2 planes, right? And one is x plus z equals 4. And the other one is 2x minus y plus 3z equals 3. Okay? Now, if we're going to have these things both be true, we're going to need to substitute one on the other. So I've seen this one is looking really nice. So I'm going to just solve for x in terms of z. And then right here, I'm going to plug in on that x. And I'm going to say, well, that's 2 times 4 minus z is going to be 8 minus 2z minus y plus 3z equals 3. Okay, clean that up for a second, and that'll be z minus y plus 5 equals 0. So maybe I could solve for y in terms of z. I've got x in terms of z. I could solve for y in terms of z, and then I could let z be my free variable. And then after that, well, I could, just write an equation for a line. That has one free variable, okay? So let me just show you what's going on. All right, so I'm going to solve for y and say y is equal to, I'm going to add it over here, 1z, subtract the 3, that's plus 5, okay? So x depends on z, y depends on z. Z seems like it can be whatever it wants, right? But one free variable as lines, seeming good. So I'm going to say, let z equal t, right? Then I've got my line defined by, well, x is equal to 4 minus z, which is t, so 4 minus t. Y is z plus 5, so it'll be t plus 5, and then z is t. Okay. And that's an equation for a line. Okay. Number 7. Oh. Let u and v be non-zero vectors with length of u equals length of v. So that u plus v is orthogonal to u minus v. This one, I don't know if I meant for this to be the last question, and I just found some other ones I wanted to add on. But this is definitely like the challenge question here. This is like kind of a step beyond what we typically do. This is a step beyond computation level of linear algebra. Okay, so length of u equals length of v. Okay, I'm still not sure if I'm going to want to show you the whole thing here. Let's see. Okay, which means, let's see, I remember when I was looking at this problem, I worked it off to the side and I was able to prove it, so I should be able to do it now. That means that u1 squared plus u2 squared plus all the way to un squared is equal to the same in v. Okay, and I mean, really, if the lengths are the same, then these square roots are equal, but that if the square roots are equal, then, their respective squares would be equal, so I can just say that, right? And u plus v is equal to u1 plus v1, u2 plus v2, all the way down to un plus vn. Yes, I see where we're going here. Then u minus v is equal to u1 minus v1, u2 minus v2, all the way through un minus vn. Pardon me, my head bumped into the document camera. And then we're going to, if we want to show that two things are orthogonal, we had better sure dot them and hope it comes back to 0, right? That's what we know. All right, so let's look at, you know what? I just realized that something I told y'all recently in class about the distributive property of dot product is going to make this much easier. But, okay, if I was to dot these, man, I feel really silly now. If I was to dot these, on this level, it's going to be a lot of like difference of squares, right? It'll be u1 squared minus v1 squared. So I'm gonna grind through all the way with the algebra, and then I'm gonna show you using the distributive property that this is just much easier. Kind of go straight to that. Anyway, u1 squared minus v1 squared. Maybe I'll put them in parentheses. u2 squared minus v2 squared. More. But then, well, let's scoot that over a little bit, un squared minus vn squared, right? Okay, But if we were to just arrange them all with a u1 squared plus u2 squared plus u3 squared all the way through un squared, minus the corresponding v's would be v1 squared plus v2 squared all the way up to vn squared. And we said up above that these two quantities were equal, so if I'm going to subtract them, that's going to equal 0. Okay. Alternatively, a person could have said from here, maybe I'll switch up color to pink, using the distributive law, this would be u dotted with u plus u dotted with v minus u dotted with v plus v dotted with v. No, pardon me, that's going to be a minus v dotted with v. And this, oh, showed up. Minus v dotted with v. Okay. Now, these are going to go away. And I'll have u dotted with u is length of u squared, minus v dotted with v is length of v squared. They have the same length, so their squares of their lengths is going to be the same. If that's going to be 0, means that they're orthogonal. Okay, yeah, I'm going to feel like a dummy now. I was working way too hard up here. Okay, so that distributive property, it comes in handy oftentimes when we're trying to like prove stuff, right? But who knows, maybe in a problem-solving environment you'll need to use that as well. Okay, so sketch the graph. Oh, no, there's a number 8 that I have not done. So let's right over here. Number 8 is going to be passes through 2, 3, 4 and is parallel to the xz plane and the yz plane. All right, so I'm going to have to draw this for you. So there's my xy plane. Here's the z-axis. Okay, so if we're going to talk about, what is it, xz plane. Okay, xz plane, just to give you a little picture of it. I'm going to get a couple more colors. I'm going to get like a blue and a green, I think. Maybe a blue and a red. Blue and red's what I got. Okay, xz, I guess I might want to put a little z in here. Okay, the xz plane is this. Okay, and then the yz plane, right, yeah, yz plane is going to be this one. Okay, and then this is going to be the, what I would call the xz plane. This pen is messed up. Okay. Let's see. All right, if it's parallel to both of those, it's got to be in the xy plane, right? If it's parallel to some things, then that means it's not going to be like intersecting them. Let me think about this. Oh, no. No, if it's parallel to both of these, I see what it's going to need to be. And just kind of look at your thing. If it's parallel, it can't intersect either of those, right? And so I'm looking for a big green pen. I'm going to hope for the best with this one. It's going to need to be, like, very vertical, right? Okay, it's going to just really be, it's the type of thing, it's like the z-axis where x and y are set and z is allowed to roam free. So what it's going to be is, I guess x and y have to be the same as 2, 3, 4, and maybe I'll even, I'm kind of running out of colors here, but, you know, 2, 3, 4 might be up here. You know, 4 units above that spot. And that means that if it's parallel to both of those, it's going to just go right down. It's not in the xy plane, it just really passes orthogonal to the xy plane. Okay, So really, this is the equation, or the line where x is set at 2, y is set at 3, z is allowed to be 4 or any other real number. Okay, so this line is going to be 2, 3, t. You could call it 4 plus t, you could call it 4 minus t, really, just as long as that's free to be any real number. All right, and okay, what else was I thinking? I thought I had something else to say about that, but okay. Sketch the graph of the plane, label the intercepts. We can definitely do that. That's not something I showed you how to do, but well, here I am. I'm going to show you how to do it now. All right, 4x plus 2y plus 6z equals 12. Okay, these are all, these are all going to have, when I solve for the intercepts, I'm going to have positive numbers for each of those. So this is, I'm going to want to kind of change around my perspective so that positive x, y, z is not in the background, but in the foreground. Because, right, in the foreground of this image is where x is positive and y is negative. So, it's kind of a natural way to think about the x, y, z space, but it doesn't really help you draw good pictures of planes. So what I'm going to do instead, and maybe, because I got plenty of time, it's not time crunch scenario, I'm going to draw something like this. Something looks like a tripod. And let's see, which one's going to be? Yeah, z is going to be the one that ends up being 2, so I don't need that much z-axis. And, okay, you got to kind of change your perspective. We're looking from the positive direction, so this is going to be my x-axis, that's going to be my y-axis, and this will be z. Okay, and then, well, to find the intercepts, I'm going to say the x-intercept, and I'm not going to do this each time, is where, say it's here, which I am going to let it be there. That's where y is equal to 0 because the y-axis keeps going that way, right? That's negative y, this is positive y. And z is 0 because this is where z is 0, that's where z is positive, and down here is where z is negative. Okay, so y and z are both 0, meaning 4x equals 12 and x equals 3. Okay, for the y-intercept, I'm going to have 2y equals 12, y equals 6. And then for the z-intercept, I'm going to have 6z equals 12, z equals 2. Okay, so that's going to be 2. Put that above because I know that the picture of the plane is going to come in. And since I've already used the straight edge once, maybe I'll sketch it in red. Color that green. It's a nice heavy marker. So we're just going to connect the dots. Have it. It's a really nice sketch of that plane. And if we wanted to, give it some perspective, we could give it a little bit of that. And that's real nice. Okay. And you can envision it extending into other areas, but we can't draw it doing that. It has to stop somewhere on our drawing. So might as well draw it like that. Okay. And the next semester, we'll be able to find that volume. Although I think you could probably find that volume right now if you tried real hard. So that's how we're going to sketch a plane. We really like it when the intercepts are all positive because then it lets us draw it real nice like that. But, we'll get some other practice on that. Let's see, what was I going to say? All right, not sure what it was. Okay, the last two are a little extra. I think the 10 is not much, but number 11, these find the distance type problems, those can be a little tricky and you just need to draw your pictures. But for now, I think 10 let's see, f is a plane 3x plus 4y minus 5z equals 1. Okay, so we know that is the vector n equals 3, 4, negative 5. All right. And with this, that's the first thing. Find values of a and b that would make this plane parallel to f. All right. Parallel to f is going to be having the same, like the same, what's this called, normal vector. But, you know, if it was 3x plus 4y minus 5z, it would have to equal 0 or equal 3 or something not 1. So they would be parallel and not the same plane, right? And so what I'm going to say is for a, 6x plus 8y minus 10, plus az equals b is a parallel plane. So maybe I'll just, hold on, yeah, I think I'll draw the top one first. And then you kind of just, if you want to have another one like that, they're going to have some space in between them. So, but to have the same normal, right, because the normal is coming out of this one, it should probably be coming out the bottom of that one too, if they're parallel. I need these, you know, at least the normal vector to be proportional. So a is going to be negative 10. And b is really anything besides 2. So if they said, give me an example, just give me values of a and b, I'm going to say b equals 0. All right? And it goes through the origin. And I know that this one does not go through the origin because when x and y and z are all 0, it says 0 equals 1. It's not part of the plane. All right, b. Find the value of c that would make the plane 5x plus 5y plus cz equals 0 orthogonal to f. Now, if two planes are orthogonal, now I don't think I'm going to try to, well, hold on. I have drawn a picture of two planes that are orthogonal earlier, and I'm going to go up here and look at it. If these two planes are orthogonal, then here's a normal vector to that one. And here's a normal vector to this one, right? I don't know if you can tell, but I think it's pretty clear to see that these normal vectors are themselves orthogonal. So I'm going to just say that this normal vector needs to be orthogonal to the normal vector on this thing. So if I want, yeah, let's say those are my planes, right? I don't know. Did the best I could. Okay, if these planes are orthogonal, then it will be the case that 3, 4, negative 5 dotted with 5, 5c needs to equal 0. Okay, so I've got 15 plus 20 is 35 minus 5c equals 0. So 35 minus 5c equals 0. I think that's going to need to be c equals 7. All right, now let's see if I can fit the third one in here. Angle of intersection between the plane and f. Again, I think that the angle of intersection between the normal vectors is going to be the same as the angle of intersection between the planes. It'll just be like kind of off by, or the vectors will be off by 90 degrees, but their relationship will be the same as the relationship between their, corresponding planes. So I'm going to say angle of intersection between this, I need to just find angle between 3, 4, negative 5 and what's the other one? 1, negative 1, 10. So what we need to do is we need to find the dot product and then use the cosine property. And so the dot product is going to be 3 minus 4 is negative 1, minus 50 is negative 51. And that's going to be negative 51 divided by That's an interesting thought. Do two planes really ever intersect obtusely? I guess it's up to your perspective, and I'm not sure what about our perspective on these is going to make it, because we can see it's going to be a negative product making... Oh, I guess it was like, one of these, we could have made this one positive, right? Or we could make -1, +1, -10, and then we would have had a positive dot product, and we would have gotten the acute angle. So at some point, at a certain level, it doesn't actually matter. Whether you've got the obtuse angle or what would it be, supplementary acute angle. Okay, length of this thing is going to be 9, and 16 is 25, and 25 is 50. Length of this is going to be 102. Okay, so I'm going to just solve for the nearest number of degrees. All right, so let's see. Let's get in degree mode here. And maybe I can put on math print so we can make it look nice. So I'm going to take inverse cosine of a fraction. Yeah, there we go. -51 divided by the square root of 50 times 102. We're in degree mode, so 135, 136 degrees. Okay. That's the angle of intersection between the two planes. All right. Now the last one is find the distance between the two planes, find the distance between the point and the plane, point and line, line and line. And, well, these are ones that I had to work on my own to just like refamiliarize myself. These actually came out of the calculus textbook, but I'm going to just try to draw you all the pictures and give you all the explanation here. All right. First is going to be distance between two parallel planes. And this one is maybe not quite as easy as you want it to be. We're not going to be able to say like, oh, this one equals 10, that one equals 6, the distance is 4, unfortunately. That would only be if they were somehow like, the XY, two versions of the XY plane, like Z equals 10 and Z equals 6, that would have a distance of 4. But this one is not going to play out like that. All right, so let me just get back to it. I'm just going to write them, and then I'm going to try to draw the picture for you, okay? Because I still think a picture would be helpful here. Okay, so the plane is x minus 3y plus 4z equals 10, and the same equals 6. Okay, what we're going to need, I'm going to draw let's see, do I really... Oh man, that was whatever. Okay, so what we're going to do is we're going to find a point that happens to be on each plane. Okay, then we're going to find the vector between them. But as you can see, like if we just take 2 points that we just happen to find on there, we don't know that it's exactly... that one's right exactly above the other one, especially with respect to the plane. So I think that we're going to need to work with the normal vector, and we're going to place the normal vector right below this one. But first we need to get some points. I think for, and maybe I'll say that this is the blue plane, and this is the red plane. That might be good for reference. Okay, so one point on the blue plane that I can see right now is where x is 10, y is 0, and z is 0, right? Okay, and on the red, let's say x is 6, y is 0, z is 0. Okay. And you might be like, wait, these points are 4 units apart from each other. But again, we don't know that with respect to like kind of the tilting of the plane or whatever, that's the shortest distance between the two planes, right? This just means that the z-axis, I guess the x-axis is this. This is the x-axis, right? The line that connects those 2 points. But what we need to do is we need to get a vector here. Call that V. So V looks to me from red to blue is going to be, I didn't actually label this, but I think it's going to be 400, right? Yeah. So that might be nice to work with, and that was kind of why I chose those points. So now I've got this, but then I've also got the normal vector out of this plane. Okay, and what I'm feeling like is I actually want, well, let's just look. And that's going to be the normal vector, which is equal to 1, negative 3, 4. So what we want to do is find, oh, wouldn't we want to project? Oh, okay, I see. Okay, that I drew this vector really too idealistically. Maybe, we don't know, maybe that's n right there. Maybe that's 1, negative 3, 4, okay? The idea here is that we're going to need to project v onto n, right, to find the distance. Yeah, because, yes, we're going to project v onto n. And that's something, that's a formula I forgot to show you. I mean, it was in the pre-calculus course, but I'm going to need to go kind of just like dig that up and show you. All right, so as a side note, kind of like down here, remember that if we want to project, or if we want to dot A dotted with B like that, that's equal to the length of the projection of A onto B, okay? But in order to get that, what we would need to do is, well, hold on. I'm looking at the formula right now and trying to reconcile it. It's going to be the length of the dot product, but then I'm going to have to divide by the length of n, which I see why, because I want to make it a unit vector. I want to, it has to do with the vector projection formula. I'm not going to sit here and like fumble over it too long. I am going to just kind of go with formula. So this distance, and if you want more on this, come talk to me at the beginning of class next time, and probably by then I will have this more straight in my head, right? I can see why it is, but not well enough to really draw all the diagrams and explain it super well, I don't think. So what I'm going to do is I'm going to say v dotted with n divided by the length of n, okay? So it's going to be distance is equal to, well, I suppose really it's like the absolute value of v dotted with n divided by the length of n. Where this is the length of a vector and this is the absolute value of a number, which I know is like a little confusing. Oftentimes in textbooks they'll put double absolute values around a vector to let you know that they mean the length of a vector. But we just don't have time to be drawing double absolute value signs. I mean, that's just not going to work for us. So v dotted with n is going to be 4, right? Yeah, 4 over the square root of 16 and 9 is 25 and 1 is 26. Okay, so that's going to be the distance from the two. And, oh, hold on. I might see a different way of talking about this. All right, if I take out this triangle here, this is length of v. This is this distance that I'm hoping for. This is theta. It's length of v cosine of theta. And then there's, okay, so length of v cosine of theta equals, and if this is, oh, but that's not the one we're dotting it with. That's weird. Okay, if this is, it has to do with cosine property. I'm fumbling right now. This video is really, really long, so I'm going to just be moving on to the next distance problem. All right, for 11b, we're going to go point to plane. And I think that this one's a little easier for me to draw the picture of. So for part B, I'm going to draw the plane. Okay, I'm going to put the point clearly outside of it, and you can't see that point, but okay, that's not, you know, a huge deal. There we go. So this point is, I've lost my worksheet. Okay, the point is 284. Okay, then there's going to be the normal vector off of the plane, and hold on just a second, and that's going to be, what is the normal vector going to be? Oh, 2, 1, 1. There it is. Okay, so maybe this is, I'm going to draw it like really dramatically. Oh, you can't see it, and okay, my work on my previous problem showing, so it's like, maybe that's it. Maybe that's the normal vector 2, 1, 1. Yeah. So what we need is we need a point on the plane, and we're going to write a vector here, and then this distance here okay, this distance here is what we're looking for, right? So D is going to be equal to at least the length of the projection of this vector onto the normal vector, right? Because this is parallel to that, right? Okay. So what I'm going to need to do is I'm going to need to get a point that's on the plane. So if it's 2x plus y plus z equals 5, maybe I'll say 0, 0, 5 is going to work. Okay, making our vector here that I'm going to call v, let's say v is equal to, what am I going to say? V is equal to 2, 8, negative 1. All right, and okay, now I need to, yeah, it's d is going to be equal to the projection of v onto n. And just to, on an aside, I'm just going to tell you the theorem, and I guess I'm just going to have to prove this theorem for you next time in class, right? I'm just going to give it, or you know, at the most is it's going to, I guess, be the length, yeah, because the projection is oftentimes itself a vector, right? Yeah. So, okay, the theorem is that, you know, hold on just a second. I'll grab the actual statement of the theorem from earlier in the textbook. All right, there it is. There's the relevant formulas. Okay, that's how to find the projection, which is the vector, and then we need the length of the projection, right, to find d. So what we're going to do is we're going to take, you know, v dotted with n, and we're going to divide by the length of n. Okay, so v dotted with n, and then if it's negative, we would make it positive, and then we're going to divide by the length of n. All right, so this is going to be v dotted with n. V is this, n we have somewhere, don't we? 2, 1, 1. Okay, I don't think I've written that, but okay, their dot product is 4 and 8 is 12, minus 1 is 11. Divided by the length of n is 4, 5, 6, so 11 over the square root of 6. Okay, that's point to plane. Third, we have point to line, and this one requires a little bit of trickery also, and oh, it has to do with the sign product of the cross product. I think what I'm going to do is, all right, if we have a direction vector, I'm just going to copy the theorem, and again, if you are interested in the proof of this, come talk to me. This isn't like the most important thing ever in linear algebra, though. I just really wanted to do some algebra with points and lines and planes, and then I may have taken it a little too far. So I'll just copy the theorem for you real quick. Okay, there it is. That's the formula. Again, if you want more, come talk to me and I'll work with you probably outside of class, but I'd be happy to go through the derivation of this. Okay, so you've got a point that's off of a line, right? You've got a direction vector on the line or in the direction of the line, and we've got a point on the line. So that's one thing we need to grab is a point on the line. Let's choose t equals 0, and so that'll be or maybe t equals, I'm going to choose t equals 1 for p, t equals 1, and we get the point 4t minus 2 is 2, y is 3, z is 0. Okay, 2, 3, 0. Okay, then q is the point 2, 8, 4. It's the statement of the question. And then u is the direction vector for the line, so that's going to be 4, 0, negative 1. Right? So it's going to be, I just follow the formula, PQ is 0, 5, 4. Okay, so that cross product is going to be PQ crossed with U. Okay, so it'll be 0, 5, 4, 4, 0, 1, and all right, so that'd be I times 5 minus 0 minus j times 0 minus 16 plus k times 0 minus 20. That's giving the vector 5, 16, negative 20. Okay, so that's going to be, okay, I think, I'm going to just use calculators to be sure. 400 plus 25 plus 16 to the 2, which I think is 256. So that's going to be 681. Okay, the length, okay, and I need the length of the cross product. So it's going to be d is equal to the square root of 681 divided by the length of u is the square root of 17. And that's going to be good enough for our purposes here. Okay, and then the last one I've got for you, it's almost an hour long, is going to be the between two lines. All right, so do you need a formula? Maybe. So this, distance between two lines that are parallel is going to be very much like what we just did, point to line, but, we're just going to get a point on each of the lines. So if I've got, f of t being my first line, that's going to be, can you see that? Yeah, okay. F of t is going to be 2 minus t, 3 plus 2t, and 4 plus t. And then g of t is going to be 3t, 1 minus 6t, and 4 minus 3t. Okay. Now, for this one, I just need a point on each of them and a direction for, let's say, g. Okay. Yeah. Actually, maybe, yeah, let's just do that. Okay, so I'm going to have a point on f, so point f. I'm going to let t be 0, and I'll have 2, 3, 4. And a point on g, I might like t equals 1, and I'll just call that capital G. I guess really, it's a vector, it's points, same thing, but maybe I'll write it like t equals 1, so it'll be 3, negative 5, 1. Okay, and then the kind of direction vector that on the last problem I was calling u is going to be equal to the direction vector for g is going to be 3, negative 6, 3. And, okay. So I'm going to pretty much just do the same thing, right? Because this point F, we're just really finding the distance from point F to the line, to the line G of t. So I just need, let's see, on the last one we went from the line, so from G to F. So what I want is distance is the length of the cross product of GF and U divided by the length of U. Okay, so GF is going to be -1, 8, and 3. If I cross GF by U, that's going to be so 24 minus -18 is going to be 42 minus J times -3 minus 9 is -12 plus K times 6 minus 24 would be -18. Okay, so we're looking for the length of the cross product is going to be the square root of 42 squared plus 12 squared plus 18 squared, and that's, I'm going to need some support on that, I think. So 42 squared plus 144, I know that one, plus 18 squared is 2232. You know, just on the off chance that that is a perfect square, it's not. So it's square root of 2232. Okay, so equals square root of 2232 divided by the length of U, which is, this length of U, oh yeah, 9, 18, and 36 is going to be 54. Okay, I'm sure this could be simplified if we just absolutely had to, but you know, that's going to be all. You know, 57 minutes, I think that's enough of examples of points, lines, and planes in space.